Okay, so what we're looking at today is acceleration. So the thing to remember is that the big idea that we just finished covering was that if you graph position versus time, so this is position x versus time, and you, for example, walk across a parking lot where you get a graph that looks like this, the big idea was that the slope of this graph was equal to the velocity. And we spent a lot of time figuring out what that means and doing calculations, finding the slope and stuff like that. So what we're going to do today is look at what happens if you graph not the position versus the time, but what if you graph the velocity versus the time? What if you look at a graph where you're plotting not where somebody is, but how fast they're going, the velocity versus the time? And if we think about the case where we walked across the parking lot, we walked at a constant velocity. So maybe your velocity was 2 meters per second, but it never changed all the way across the parking lot. So it was actually just a horizontal line that represented the velocity versus time. The velocity never changed. But what if the velocity does change? What if you have a case like we did in lab, where we had a ramp and we had a cart on the ramp, and the cart was rolling down the ramp? What would the velocity look like then? Well, what happened was, as the cart rolled down the ramp, the position versus time graph changed in a predictable way, and that wouldn't surprise you at all. The position versus time graph looked like a parabola. It looked something like this, like that. But what we didn't look at was, what does the velocity versus time graph look like? And so that's what we want to do now. If you were to plot the velocity versus time for that cart rolling down a ramp, what would it look like? So this is going to be the velocity versus time. And remember, if we plot position versus time, the slope is the velocity, right? The slope gives you the velocity. So right here the slope is 0. So maybe it's 0 right there. Right here, let's say the slope is 1. Right there. Over here, the slope is getting steeper. It's maybe like 2. And then over here, it's getting really steep. Maybe it's something like 3 over there. So if we draw a graph of the velocity versus time, you can see that it's actually increasing, something like that. And when a velocity changes, we call that an acceleration. So, here's the big idea. If you graph velocity versus time, the slope is the acceleration. It's the rate that the velocity is changing. So that was the big idea we talked about today. If you graph velocity versus time, the slope is the acceleration. Now, let's look at that for a minute. Velocity versus time, the slope is the acceleration. So that means that if I have a graph showing the velocity versus time, and I graph the velocity of my car. Here's the velocity, here's time. My car can go from 0, let's say this is 60 miles an hour. My car can go from 0 to 60 miles an hour, but it might take a while. Let's say it takes 12 seconds. You might have a really fancy car with a big engine, and you can also go from 0 to 60 miles an hour, but the difference is you can do it in much less time. So in this case, you would say your car has a greater acceleration. Both cars go from 0 to 60, but the one that does it in the smallest amount of time has the greatest slope. And so again, the slope is the acceleration. If we were to find the slope, we would take 2 points, let's say this point right here, and we would find the rise divided by the run. The rise is what we call the change in velocity, how much the velocity changes. The run is the time, and so the slope, which is the acceleration, will actually be the rise, delta v, over the run, which is t. And that's going to lead us to our first equation. If the acceleration equals delta v over t, I can multiply both sides by t, and I can get a times t equals the change in velocity. And you guys know the change in velocity is the final velocity minus the initial velocity. We're going to use v0 as the initial velocity. And then if I add v0 to both sides, I get rid of it there, and I'm left with v final. So here we go. This is the equation we're after. V final, the final velocity, equals the initial velocity plus the acceleration times the time. That is the equation that needs to go in your toolbox, and that's the equation we're going to work with on this homework assignment. Okay, so we call that a working equation. V final, of course, is the final velocity. V initial is the velocity at the beginning of the problem. The acceleration and the time are usually given in the problem, or you're trying to find one of them. So if we look at the units of acceleration, so that you should put that in your toolbox. That sucker right there should go in your toolbox. We're going to use that all year long. It's called one of our working equations. Okay. Now let's think for a minute about the slope. If this is velocity and this is time, and we're trying to find the slope, what units would we have for the slope? Well, the units of velocity are, for example, miles per hour divided by, so that's like the difference in velocity. The time, we might have seconds. So I might have an acceleration that has, my car might have an acceleration of 5 miles per hour per second. And that's kind of a goofy looking unit, but it sort of makes sense. What it means is my car will go 5 miles an hour faster every second that goes by. So, if I made a little table, here is the time, and here is the velocity of my car. At 0 seconds, I'm going 0 miles an hour. After 1 second, I'm going 5. After 2 seconds, I'm going 10. After 3 seconds, I'm going 15. After 4 seconds, I'm going 20 miles an hour. And so, my velocity is changing by 5 meters per second, miles per hour, every second that goes by. Okay, so that's a unit of velocity. Units of velocity, if we use the metric system, would be, for example, meters per second. So I might have 3 meters per second change every second, which we sometimes write as 3 meters per second squared. So that's another unit of acceleration. So lastly, let's just solve an example problem to kind of see how this works. You can look at the example problem online, but imagine you have an airplane and it's going to take off, and it's going to start right here at the beginning of the runway, and when it gets down here, it's got to be going fast enough to get into the air. There it goes. Whee! For my problem, my initial velocity is 0 because my airplane starts at rest, so I'm going to say 0 meters per second. The final velocity required to make the airplane go is 55 meters per second. The acceleration is unknown. I'm wondering what kind of acceleration I need, and I know that I need to do this in 30 seconds. So this is what we call a diagram. This is a variable list, and you're going to make all of these. You need a plan. The plan is pretty simple. We're going to solve this equation we just wrote down, v final equals v initial, or v naught, plus a times t. We're going to solve this for the acceleration. So when I solve this, the initial velocity is 0, so I can make that go away. When I solve this for a, I'm going to divide both sides by t, and I'll get a equals the final velocity divided by the time. That's what we call an algebraic solution. Now I'm going to evaluate it numerically, and so I'll get 55 meters per second divided by 30.0 seconds, which is 1.8 or so meters per second squared. And so this is an example of how to solve the problem. It's also an example of what we're going to use for our problem solving structure. Okay, so the idea is we're going to make a diagram, a variable list. We are always going to state our plan, tell me what you're going to do. I'm going to solve this equation for this variable, do it algebraically, and then evaluate it numerically. And then the last thing we're going to do is a couple of checks. We are going to check, first of all, is it reasonable? That seems like a reasonable number. Does it have the right units? We have meters per second, which is the unit of acceleration. That's right. And lastly, are the significant figures right? We had 2 significant figures here. We had 3 significant figures here, so our answer can only have 2 because that's the weak link there. So there we go. We found a complete solution for this problem. Okay? So you can look online for the problem-solving solution format. These 5 steps: diagram, variable list, plan, algebraic solution, numerical solution. So what I want you to do is solve your homework problems using this as a template for how to solve the problems. There's 6 problems online. It won't take very long. They're pretty easy. And each problem uses this equation right here. So that's our big working equation for today. Okay, thanks a lot.